One of the things about the fast reversible that we did, when the second step was slow to remove the intermediate, we had a fast and reversible first step, and the second step is slow to give us something C. So, we said that the rate of the forward and the rate of the reverse reaction are equal, right, in the fast reversible. But what happens is, okay, you have this equilibrium, and you can imagine this as being some kind of balloon, like this. But this balloon has a little leak in it. And the little leak is this here. And so we got this balloon, which is at equilibrium, but there's a tiny leak here, and that tiny leak is losing some B out of this equilibrium that's been established in this balloon and forming C. Does that make sense? So as long as the leak is small, so as long as the leak is small, that is, this would be K2. K2 is small, small relative to these, then it's reasonable. But what happens if the leak becomes kind of big, or the leak gets bigger and bigger? If the leak gets bigger and bigger, can we still use the fast reversible? That is, we have this equilibrium between A and B. No, because what's going to happen is it's going to alter that, Le Chatelier's principle. If we start losing or leaking off B significantly, it's going to shift the equilibrium to the right and eventually form a product here. Does that make sense? So if the leak is big, or if you don't want to make this assumption, because here, is this really true? This is what's called mass balance problem, right? Mass is not balanced. Using the fast reversible, what are we saying? We're saying that the rate of the forward is equal to the rate of the reverse. This is an equilibrium, but that's not really true because we're losing some. And so when we do this, we're making the assumption that B in step one, B reverts back to A. That is all of the B, because the forward rate we made equal to the reverse rate. As an alternative to this, we could do this for every problem, because this should work, is the steady state approximation. In the steady state approximation, let's just take some simple two-step equilibrium. The first step is fast and reversible. The second step is slow, the REF, C. Here, what we say is that the rate of formation of B is equal to the rate of consumption of B. So, how is B formed? B is formed only one way, from A. And so the rate of formation of B is just equal to K1 times the concentration of A. But how is B consumed? B is going to be consumed in two ways. One of the ways is K minus 1, the reverse reaction, yielding A. If you look at just this is the fast reversible assumption, right? But now we have to worry about the leak. If we worry about the leak, then we ought to add that in. That is, we're going to lose some B due to the leak, which is K2 times B. And since B is an intermediate, then we solve this equation for B's and then substitute into the RDS. And so in the fast reversible, what we did was we just assumed K2 is so small that this term is negligible, so this plus this is just equal to this. It's a simplifying assumption, right? The SA. But if the SA is not valid, then we better account for it. Or if we don't want to use the SA, then just go ahead and use this equation. Because this, the mass should be balanced. And so let's take a look at an example of this from the book again. And that's going to be mechanism. Well, this is going slow here. Why it's so slow today? I'm sorry? 6:33. Okay, that's good. Okay. So here we look at this. What is this? This is the fast reversible, right? You know, the forward and the reverse are equal. It's fast reversible. If we were to do this using the steady state, it'd be just a little bit different. This is the steady state here. The rate of consumption of the intermediate is equal to, you know, the reverse of step 1 plus step 2. And so, you know, the fast reversible is just this balloon. Now we're looking at the leak, right? The leakage coming off step 2. Does that make sense? And then we just solve this for the intermediate, in this case N2O2, right? And then substitute there. We end up with an equation that looks like this. Now, we did this. Did we do this one? We didn't do this? Did we do the fast reversible?
Yeah.
What was the rate law that we got for the fast reversible? Was it second order in NO and first order in O2? Okay. Now take a look at this. Here. This is with the fast reversible. This is accounting for the leakage, right? But let's say the leakage is very small. If the leakage is very small, then that's K2. Let me blow this up. I'm trying to save time here by not writing anything. But maybe I should write it down. This is the leakage here, K2, right? If K2 is very small, then if this is small, then this times this should be small. And if this term is small, then we could use the simplifying assumption that this plus something small is going to equal,
You turn it on.
Chem. Oh, yeah, thanks. Okay, thanks. So after we do some substitution, some algebra, this is the equation we get. And so if K2 is small, then this term is small. If this term is small, then we can use a simplifying assumption that K minus 1 plus this is just equal to K minus 1. And then we get the original equation, that is K times O2 to the first and O to the second. Okay, but if K2 is big, then we don't want to use the fast reversible. We want to use this, the steady state, to compensate for the loss, the leakage on the balloon. Does that make sense, or do you want me to write it out? It makes sense? Okay, then let's take a look at an application of this here next. All this is doing is it's showing, when K2 is small, what happens. When K2 is small, it just simplifies into our original. When K2 is big, it does something else. So, one application of this is going to be with, you know what catalysts are? Catalysts speed up both the forward and reverse reaction by lowering the activation energy, by providing an alternate pathway. Did I do this for Lewis acid base? No? Okay, I'm going to do this. But let's take a look at one example of this here, of the steady state approximation. And that's going to be, actually, this is so slow. Let me find out what page that was. 640. One more. Looking at enzymes. Okay, so this would be, you know what enzymes are? Enzymes are biological catalysts, so it'll speed up the reaction. Substrate, they call it, this is the reactant. So the reactant comes in. Normally, without the enzyme here, the substrate reacts very slowly. With the enzyme here, it lowers the activation barrier significantly so that the reaction speeds up considerably. And so here, normally what happens is this substrate breaks up into product. These are the products here. And so we'd have to break some bond here. Well, what the enzyme is going to do is there's going to be intermolecular forces of attraction. And those intermolecular forces of attraction maybe put some tension on the substrate, weakening the bond, pulling the bond apart. So the overlap isn't as good, so the bond's a lot easier to break. When the bond breaks, we get the product. When the bond breaks, right, the electrons, or the electron cloud is rearranged, and it might not be attracted anymore to the enzyme, and it can dissociate from the enzyme quite easily. And so this is it. Enzymes are regenerated. So E stands for the enzyme, S stands for the reactant. So the enzyme plus the substrate reactant yields an intermediate. This is the intermediate here. It's the enzyme substrate complex. And then the enzyme substrate complex breaks apart, and we regenerate the enzyme. It can be reused, and we form the product here. In this, the first step is quick. It quickly attaches here. This is going to be the RDS, breaking this bond. That's going to take a little more time, and so K2 is the slow step, RDS. Well, if K2, if the second step is the slow step, then the rate of the overall reaction is going to equal K2 times the ES concentration. Right? But there's a problem. ES is a intermediate. Right? We can't have an intermediate in our rate law. And so we need to get rid of the intermediate. And so what we're going to do is we're going to do the steady state approximation. And so go ahead and make the steady state approximation. What would you write down? You'd write down the consumption. You could write it like this. The rate of formation of ES is equal to the rate of consumption of ES. And so how is ES formed and how is ES consumed? Sometimes without these enzymes, these reactions really don't occur. This is all very cartoon-like. This is more of the molecular geometry here. And these are very large molecules, these enzymes. And so they just show the bonding network here, these ribbons. Here's a substrate, some reactant. Still attaching to it. Enzyme. So what do you get? You know, rate of formation of the enzyme, I get K1 times the enzyme concentration times the substrate concentration. And then for consumption, you know, the reverse reaction, so this would be K minus 1 ES concentration, right? And then how else is it consumed? Plus K2 ES. And so here, you know, we are either going to have the reverse of the first step or the second step will leak some ES off, right? If the second step is extremely slow, then K2 is very, very small, and this term is negligible, and we get the fast reversible, right? But we aren't going to worry about that. We're just going to go ahead and continue with this. What do we want to solve this for? The ES. And so you can see in here in 1435, what they did was they just factored out the ES. Do the same thing. We factor out the ES. We get the ES concentration is equal to K1 times the E concentration times the S concentration over K minus 1 plus K2. Right? And then normally what we do is we just go ahead and substitute it. But E doesn't behave like a normal reactant does. You know? And normally we just substitute here. But the concentration of E, you know, it drops and then is regenerated, right? And so it just cycles. That's consumed, regenerated, consumed, regenerated. And so it's just cycling like this, right? Does that make sense? Because it's eaten and then spit out, eaten and spit out, eaten and spit out. And so how do we, you know, this kind of something. And so what we can control though is how much enzyme we pour in there. You know, how much enzyme do you put in there, right? That's something you could control. Does that make sense? And then let it go ahead and do this cycling. And so, but E is different because it's a catalyst, right? And catalysts speed up the reaction but aren't consumed in the reaction. Well, they are consumed, right? They're consumed initially and then they're regenerated with each reaction that occurs. And so this is where we're going to deviate. You know, in the last example, we would have just went ahead and substitute that and generated that other equation, a little bit of math. But in this case, what we're going to do is we don't want to relate it to what the current enzyme, we call this the free enzyme concentration is. You know? And so what we're going to do is this. We do this. We have this, you know, the initial enzyme. The initial enzyme is, you know, the total enzyme you mix in there. And so this is called the total enzyme. It's just how much you put in there initially, right? But during the reaction, you know, it's changing because during the reaction, the enzyme is going to be split between, you know, if I have like a mole of enzyme in there, the enzyme is going to be split between being free and being complex. And so this is the total enzyme is equal to the amount of free enzyme we have at any point in time plus the amount of complex enzyme. And that gives us our total enzyme concentration. That's this equation here. The total enzyme is going to equal the free enzyme plus the complex enzyme. Okay, then we solve this for the free enzyme concentration here. So the free enzyme concentration will equal the total enzyme minus however much is complex at the given time. And then we substitute this into that. So, actually, now substitute this into this here. And so if we substitute that, we get K1, well, the K1 times the actually, let's do this. K1 times E. Well, E now is this, which is E naught minus ES times S which is equal to K minus 1 ES. Actually, I forgot to factor that out. Let's factor that out. K minus 1 plus K2 ES. Just factor out the ES from this. Now let's solve this for ES. And so if we solve this one, oops, I forgot to do the camera. Do that. Okay, we solve this one for the ES concentration. We get that the ES concentration is equal to the equation over there, which I'll just copy to save time. K1 E naught, or E total enzyme times the substrate divided by K minus 1 plus K2 plus K1 S. All right, so that's basically what they're doing here. You got the ES, the intermediate concentration. All right, now that we have the intermediate concentration, we'll just put it in the rate law. V just stands for velocity or rate. So the rate is equal to, now we do some more substitution. We substitute the ES back into the original rate law. Right? And we end up with this. Okay. Let me erase this. We'll continue here. So we're going to substitute into the RDS rate. The RDS, the rate was just equal to K2 times the ES, right? And so this is going to give us, well, we just do K2 times that is just going to give us K2 times K1 total enzyme times S divided by K minus 1 plus K2 plus K1 S. What we'll do is we're going to combine some constants here. We're going to combine, We're going to combine K minus 1 K2 over K1. I'm going to call this Km, capital Km, or 1 over Km. And so when we combine those, then we're going to get K2 total. You don't have to do this derivation. Km plus K1 S. So actually, I need to factor it out, sorry. Factor that out. K minus 1. What was it? K minus 1 plus K2 over K1. K minus 1, that's it. Well, I should have skipped steps. Otherwise, it's harder to follow along. But, you know, eventually you go through this and you'll get this equation. And so the basic point to remember for this is this. This is a steady state approximation with one additional twist. The one additional twist is that we're getting this in terms of total enzyme rather than free enzyme concentration. And so that's why this one's a little more complicated than your normal substitution. Now you don't have to do this derivation, but you should understand this equation. And this equation works like this. It's first order in the amount of enzyme. So, you know, if we double the amount of enzyme, what should happen to the rate of the reaction? It should double. And so the more enzyme we have in there, the faster this reaction should proceed, even though it's not really being consumed. But likewise, if we double the amount of substrate, what happened? Well, if we double the amount of substrate, that's more complicated, right? Because this equation has substrate in the numerator and the denominator. And so the way we can visualize what's happening here is by looking at this graph here. This graph here. This graph plots the reaction rate versus the concentration of the substrate. And what happens is the reaction starts off as first order, and then eventually converts to zero order. And then transitions to zero order. And so what's happening here is this. If we double the substrate concentration, the rate should double. It's 2 times. Up to a point, around here we run out of enzyme. If we run out of enzyme, that is, when we run out of enzyme, it's cycling at its peak as fast as it can cycle. And this is like the phone booth. There's a phone booth analogy. Like, say there are a bank of phone booths or phones, pay phones. And so here, if you're trying to make a call, or doors, it could be doors. If you double the number of people trying to make a call, you get twice as many calls. If you triple it, you'll get 3 times as many calls. But eventually, what happens is there's a cycle time. Each person takes some time to make a call. And pretty soon you're going to saturate all the phones. And so things are going to have to back up. And so you've reached this peak. Well, it doesn't matter if you double it now because there aren't enough phone booths to take care of all the people. And so this is why there's a switch here to a zero order. And so what happens here is this. We can understand this in terms of what's happening with Km and S. At sufficiently low concentrations of S, then if S is small compared to Km, then what we can do is we can ignore. Km is negligible compared, S is negligible compared to Km. And what does Km contain? Well, Km contains K1, K minus 1, K2. K minus 1 and K2 are consuming the enzyme substrate complex. K1 is forming it. But anyway, what we get is this. The S term drops out of this, and we get first order in enzyme and first order in substrate. And so here, when S is fairly small, that is, there aren't that many people trying to make a call, then it's going to be first order. But if S grows big, what happens is the reverse of the simplifying assumption happens. And so if we flip these arrows so it's reversed, then what does that mean? It means that S is big relative to Km, and Km is negligible. If Km is negligible, then the S's cancel each other out, and we get zero order in S, first order in enzyme. And so the only thing we could do to speed up the reaction here is just double the enzyme or increase the amount of enzyme. And so this is just an application of steady state approximation with an additional work. This is a very famous equation, and so this is why I wanted to show it. This is the Michaelis-Menten equation for enzyme kinetics. So this is very important in biochemistry. Surprisingly, when I took biochemistry, we did so many kinetics labs, lots of kinetics labs. Why? Because they're very interested in the mechanism for biological reactions. So that they can get some insight into the mechanism of these reactions. based on the kinetics. And so let's take a look at some homework problems here and then see. Maybe I'm just going to flip to the page. So soon. Page 651. Oh, why this is so slow today? What's that?
Is it Wednesday? Oh,
Okay. All right. So if we look at number 83 here, you know, the following data are for the reaction 2A plus B yields products. Oh, actually, that's not the one I want. 79 is the one I want. All right, let's take a look at number 79 here. The hydroxide ion is involved in the mechanism of the following reaction, but it is not consumed in the overall reaction. And so when you think about hydroxide, if hydroxide is involved but it's not consumed, then hydroxide must act kind of like a catalyst. You know, it's being consumed and spit out again. So this is why they draw it over the arrow here. And so they're taking hypochlorite and iodide, this is a redox reaction, to make hypoiodide and chloride. From the data given, determine the order of the reaction with respect to hypochlorite, iodide, and hydroxide. And so let's take a look at the data here. You know, let's take a look at this 40 to 20, 20 to 40. That's too complicated. Let's find something simple. Something simple would be like this experiment. If you look at this experiment, 20, 20, and then this experiment above that. So we keep the hypochlorite the same, but we double the iodide, and we keep the hydroxide the same. And so if we double the iodide, what happens to the rate? It doubled. So it's going to be first order in iodide. First order in iodide, and then let's look at these two here. You see I'm doubling the hydroxide but leaving everything else the same? So if I double the hydroxide, what happens to the rate? Cut in half. If it gets cut in half, do you know what order that is? -1 order. So double the hydroxide, 2 to the -1 is 1/2. Does that make sense? And so that means it's -1 order in hydroxide. And let's see, we need to find out the order with respect to chloride. And it looks like this is the only case where we double. We double the chloride here, and this one here. So double the chloride, leave these the same. What happened to the rate? It doubled, so it must be first order. So what did we say? First order in hypochlorite, first order in iodide, and -1 order in hydroxide. So 79. We have the rate is equal to K, and this is going to be first order, and -1 order. Okay, what is the overall reaction order? 1. This is first order overall. Write the rate equation and determine the value of the rate constant K. So what we do is we figure out what K is for this. We figure out K for this, K for this, K for this, K for this. So we do 5 calculations for K and then take the average. Does that make sense? Because here the rate is equal to K, so K is just equal to the rate divided by the concentrations, raised to the respective power. And so for each experiment, we're given the rate and the concentration. You just plug it into that equation, solve for K, get the average K. We can determine K. So is that good? All right. now we go here. Show that the following mechanism is consistent with the rate law established for the iodide hypochlorite reaction in exercise 79. And so in exercise 79, we have hypochlorite and colliding with the water. Well, water is a solvent in this case. Yielding HOCl and hydroxide. What kind of reaction is this? This is acid base. In fact, this looks like the Kb equation for hypochlorite, doesn't it? And it is. This is the Kb equation for hypochlorite. And so that seems like a reasonable collision, doesn't it? I mean, you expect this collision to happen for sure. Okay, let's take a look at the next reaction here. Next reaction, or next step, is iodide and hypochlorous acid builds hypoiodous acid and chloride. This is, they're calling the slow step here. Followed by a fast step. And so the RDS for this reaction is going to be the middle one here. And so that's what we care about. And so what we're going to show is that this is consistent with this rate law. And so to show that it's consistent, then the rate law has to match. You know, the rate law we get from the mechanism. The rate law we get from the mechanism is rate is equal to K2 times the iodide times the hypochlorous acid. All right, now what do we do? We need to get rid of the intermediate. Now, how should we get rid of the intermediate? Should we do the fast reversible or the steady state? Well, this is an advanced problem, so we probably should do the steady state. Otherwise, it'd be too easy, right? So let's do the steady state approximation. The steady state approximation is that the rate of formation. How is HOCl formed? It's formed from K1 times the hypochlorite times the water concentration. How is hypochlorite consumed? This should be K minus 1 here. It's going to be consumed by K minus 1, the reverse reaction, times the hypochlorous acid times the hydroxide. And it's consumed by K2 times the iodide times the hypochlorous acid. And then what do we normally do? We just solve for the intermediate. The intermediate in this case is hypochlorous acid. So hypochlorous acid concentration will equal K1 times the OCl minus concentration times the H2O concentration divided by, we factor that out, we're going to get K minus 1 times the hydroxide concentration plus K2 times the iodide concentration. Okay, now what? Now we substitute that in there, right? And so we get that the rate is equal to K2 times the iodide concentration times K1 times the OCl minus concentration times the H2O concentration divided by K minus 1 times the hydroxide concentration plus K2 times the iodide concentration. Is that what we have so far? What are we going to do with this water? Yeah, this is free water. Water is a solvent. Do you know the molarity of pure water? 55.5 molar, roughly. Do you think we're going to consume much water in this reaction? No. And 55.5 is huge. And so water can be considered, the concentration of water can be considered pretty constant. Yeah, so what if we have a little bit of solute dissolved in there? It's still mostly water. And so what we're going to do is we're going to incorporate water into the constant here. We'll call it K prime. Actually, we'll add these constants in here too. So we got K prime times the iodide concentration times the OCl minus concentration. We'll combine, actually we can't combine those yet. Over K minus 1 times the hydroxide concentration plus K2 times the iodide concentration. So now what? It still doesn't match, does it? No, it still doesn't match. Well, we want the hydroxide concentration in there, but there's something else, though, that we don't necessarily want. That's this other term here. It's K2 iodide. Right? And so it doesn't seem consistent, does it? It doesn't seem to match unless we make some kind of assumption. What assumption would we have to make in order to get it to match? We'd have to assume that K2 is very small. That is, K2 is very slow. If K2 is very small, then this term plus this term, we could use the simplifying assumption. This term plus this term would just be this term, right? Does that make sense? If K2 is very small. So if K2 is very small, then this simplifies into K prime iodide times the OCl minus over K minus 1 times the hydroxide. And then we'll just combine these constants and we'll get K double prime iodide times the OCl minus times the hydroxide to the minus 1. Then it seems to work out okay as long as K2 is quite small. Okay. I want to do some others. We should take a look at some of these mechanisms in general, just to see some examples of more mechanisms. The more examples you see, obviously, the easier it becomes. But look at this one here. What kind of step is that? This is a 3-step mechanism here. The following 3-step mechanism has been proposed for the reaction of chlorine and chloroform. And so you look at that, you would see this is a unimolecular step, right? And chlorine is breaking up into atomic chlorine, right? Cl2 going to 2Cl. Then we look at this next step here. We have atomic chlorine reacting with chloroform to produce HCl and this. This is a free radical. You know, it's not complete. This was a free radical here. And then this free radical, back to this other chlorine form, carbon tetrachloride. Here are some numbers here. K1, 4.8 times 10 to the third. K minus 1, 3.6 times 10 to the third. K2. K2 is small. Look at it. This is 10 to the third, this is 10 to the minus 2. That's 5 orders of magnitude smaller. 5 orders of magnitude smaller. And so K2 is going to be very small here. K3 is pretty large. K3 is fast. And so derive the rate law. The rate law for this one is complicated because what is the intermediate here? The intermediate is chlorine. But this is more complicated because in the last one we did, you know, rate of formation is equal to the rate of consumption. We only consumed it in 2 ways, right? In this one, we have 3 ways that this is consumed. Do you see that? 3 ways that this is consumed. Because it's consumed by the reverse, that is K minus 1. It's consumed by K2, and it's consumed by K3, which screws everything up, right? Do you see how that would screw things up? And so how do they handle this? Well, you know, they're handling this by giving you the numbers here, and you're going to have to make some assumptions to be able to solve this. Otherwise, it's too difficult to solve. And so why don't you look at how, or what kind of assumption you might have to make with these numbers in order to solve this. I don't know, did I assign this one? 87? I can't remember. I've assigned it in the past. Okay. Take a look at another mechanism here. Here's another 3-step mechanism. Here's a bimolecular collision, HBr and O2. HBr and O2 forms HOOBr.
No.
I didn't? All right, that's fine. HOOBr. You know, this is what people do.
Wait, chapter 87?
Chapter 14.
Yeah.
I assigned it? Yeah?
Yeah. 87? No. Yeah, you did.
I did.
Yeah.
All right. Yeah, it's hard. A lot of people will just skip that one. You know, sometimes what people do is they don't assign it and just give it as an exam question. It's a more challenging exam question. But I don't know how to do that. Well, anyway, going here, HBr and O2, this is kind of weird because what is that? An OO bond. This is called a peroxide bond. Peroxide bonds aren't necessarily very stable. But they can form, and so we form this kind of weird thing. This forms HOBr. HOBr is this hypobromous acid. That's fine. Hypobromous acid and HBr forms water and bromine. So here's a 3-step mechanism. And you know, the rate, experimental rates, first order in HBr and O2. And so does this agree with that? This is a bit tricky too because here, you know, the decomposition of nitric oxide occurs through 2 parallel reactions. And so, did I assign number 95?
Yeah.
Yeah. And so this is a bit tricky because, you know, how are we consuming it? We're consuming it in 2 ways. And so what a lot of people do is they treat these separately, but you can't treat them separately, right? Because both will decrease the NO. And so this is like, you know, when we have multiple equilibria, you know, the way I think about this problem is sometimes, you know, with multiple equilibria, you might be able to solve them separately if there's no connection between the 2 equilibria. You know, maybe they're just in the same container, but 2 totally different equilibria. And so you could solve those independently. But if there's a connection between the 2 equilibria, then you have to either solve it stepwise, simultaneous or combined. And so when we have this, something like this, you got to start thinking, how do you do this? Do you do it stepwise? Do you do it, well, how do you think you do this? Combined, I guess. If you combine it into one equation, then what do you do with these? These are rate constants, right? You just don't add or multiply the rate constants. And so you have to do this simultaneous for this particular step. Okay, there's one more homework I just wanted to briefly look at. And look in the book for this one. And that is ozone, decomposition of ozone, which is, what problem was that? Sometimes you have to propose mechanisms, These are all the mechanisms that people propose. And so when we're looking at ozone, ozone decomposes into oxygen. So if we take 2 ozones, we'll form 3 oxygens. So the overall reaction is 2 ozones yields 3 oxygens, like this. Now, let's try to figure out a mechanism for this. Maybe this occurs as a single step. If this occurs as a single step, what would it look like? Well, it'd just be an ozone colliding with a ozone, right? Number 70. So the mechanism for this, if this were a single step, then it'd be simple. A single step would have a rate law that looks like what? What would the rate law be if this were a single step? Well, go ahead and do that. We'll figure out what the rate law is going to be. I'll be right back.
Probably 70.
Oh, you're
Yeah,
70.
70. Yeah. He said 70, but he wrote 7. Because I wrote 7. Yeah.
Is that all you got to get? This is going to be Oh, yeah.
Okay, so what was the rate law then? What was the rate law you'd get if that were a single step? Does somebody have it? No? When you have a simple elementary step, what is the rate law equal to? K times the concentration raised to the coefficients. So does anybody know how I got the rate of the RDS? That didn't make any sense at all? Like, for example, I said that the rate for the enzyme one was K2 ES. Anybody know how I got that? You have this in your notes? Rate is equal to K, A to the little a, B to the little b. Do you have that in your notes? What was all that about?
Elementary process. This low.
What's the difference between an elementary process and just some reaction that's been written?
The elementary process is one step of the reaction, where a reaction could consist of.
Exactly, yeah. When it's only one step, then if it's just one step, like if this were just one step here, then what happens if I double the left ozone? What will happen to the number of collisions with the left ozone if I double it? It would double. Double the number of collisions. What happens if I double the right ozone? It doubles. So if I double ozone, it doubles both the left and the right ozone, which means it's second order. So if this were just one step, the rate is very simple. The rate is just equal to K ozone squared. It's the same as the coefficient here because it's just a simple collision. But, you know, we don't know here, for example, methane plus 2O2 gas yields CO2 plus 2 waters. If I double the methane, am I going to double the number of collisions? We don't know because we don't know what the collision is because there are so many collisions hidden here. And so how do you know the difference between an elementary step and a normal reaction in which there are multiple steps? You can't tell the difference. And so you're told that this is an elementary step or not, right? Sometimes you can't tell the difference. Sometimes you can tell the difference. And so here, this could have been an elementary step. 2 ozones collide, forms 3 O2s. That could have happened, right? Boom, you know, breaks up into. But when we look at the experimental rate law, could it be an elementary, one simple step? No. It must be more complicated. And so to just take 2 minutes to try to figure out, if it doesn't happen in one step, propose a 2-step mechanism that consists of a fast, reversible first step, followed by a slow second step. So come up with a fast, reversible first step and a slow second step. Just try it right now. The first step could be, unimolecular or bimolecular. It wouldn't be termolecular, trimolecular, because there aren't 3 ozones here. Anyway, those are lower probability. Sometimes you'll see those in mechanisms. But not common. So you're going to have to use, well, what do you have to use? What kind of knowledge do you have to use for this? You have to use knowledge of Lewis structures, stability, reactivity. You're going to have to use structure and composition, structure primarily because the composition is oxygen, to kind of figure out where it might go. When somebody has a first step that, let me know what you got for your first step. To 3 oxygens? Okay. Ozone breaks up into 3 oxygens. Like this? Okay, does this, using your structural knowledge, does this look very good to you?
No.
No, but I've seen it. How about this? That looks better because I've seen oxide. No, why not? The charges. Yeah, I've seen this too on, sometimes I see very bizarre stuff. But what you want is something that might look more familiar, would be O2 and atomic oxygen. That seems reasonable. Is ozone very stable? No, so this should be fast because ozone is stable. And it could be reversed, because... And so that seems reasonable. And then what's your step 2? O3 plus atomic oxygen yields 2 O2s. Okay, this would be the RDS. So what is the rate law for the RDS step? What is the rate law just for this step? The rate of the overall reaction has to equal the rate of the RDS.
Wait, if we add one more O2 to both sides of that, that's what we want.
No, because we have it. We add these 2. When you add step 1 and step 2, what do you get? You get 2 ozone. The oxygens cancel out, and we get 3 O2s. Because we had 1 here and 2 here. And so we add up all the products, add up all the reactions. And so the net reaction is the same. 2 ozones goes to 3 O2s. That's what we want. And so that looks good. This mechanism is looking good so far. Now we just got to test or check. I spent too much time on kinetics. I need to move on. How would you do this? Well, let's put this one I assigned for your homework. And so you figure it out. Yeah, this is a good one. You don't want to do everything. But we need to move on to chapter 19. I just want to... What time do we go till? 55? All right. At least we'll go for 10 minutes. But I think you can do this because we just did like 3 of them or something. It's very similar. All right, chapter 14 deals with kinetics. Chapter 15 deals with thermodynamics. And kinetics and thermodynamics are different, but related. Kinetics tells us the, what? Kinetics tells us the speed of the reaction. Thermodynamics tells us the driving force for the reaction. And so we need both. So we're dealing with chapter 19, thermodynamics part 2. Part 1 is way back, Chem 1A. In order to predict reactions, you need to have both thermodynamic and kinetic knowledge of the reaction. And so let's say we need both thermodynamics, thermo, and kinetics. For predicting reactions. This is the second time I'm mentioning this. When was the first time I'm mentioning about kinetics and thermodynamics? Probably don't remember. No, I did in Chem 1A, but in this course, Chem 1B. Do you remember when I first talked about kinetics and thermodynamics? Probably not, because it was the PowerPoint. It would be fast. But it was the first week. Look at the PowerPoint. One of the PowerPoint slides says we're just looking at the thermodynamic driving force. In order to properly predict reactions, we need to look at the kinetics too. Because in thermodynamics, we know that what's more stable, diamond or graphite? Diamonds are more stable than graphite? Graphite's more stable. And so what we say is there's a driving force, a thermodynamic driving force, because in nature, things tend to go from higher energy to lower energy. And since diamond is a high energy form of carbon, and graphite is a lower energy form of carbon, then there's a thermodynamic driving force for this, right? We say driving force is present. There should be reaction. And so this would be a delta H less than 0, which is exothermic. Exothermic is good. But if you said diamond's more stable, you really wouldn't be wrong, because diamond is very stable, right? And why doesn't diamond decompose into graphite? Because of kinetics, not because of thermodynamics. Kinetics prevents this from. And so we say that diamond is thermodynamically unstable. Thermodynamically unstable. But kinetically stable. And so we can put this together. If we go back to the reaction profile, do you remember this reaction profile or progress of reaction? What we do is we plot out the energy on the y-axis, and on the x-axis we have something called the profile, reaction profile, which is just the progress of reaction mapped down. And so if we start off with diamond over here, it's not just a downhill ride to graphite. I'm going to put graphite over here because later on we want to form some graphite. Both are forms of carbon. The problem is if you think about diamond, what kind of bonds are in diamond? Use valence bond theory to describe the bonds of diamond. Well, you need the structure. Diamond has a tetrahedral, a lattice network. This. Let's go this way. These are all sp3. It just goes on and on. And so diamond consists of sp3 carbon atoms. Graphite consists of these sheets. They look like benzene rings. They're all sp2. sp2 carbon. And so to go from sp3 to sp2 carbon, what has to be done? You have to break the bonds and form new bonds, right? Well, how much energy does it cost to break the bonds in diamond? A lot. A huge amount of energy. And so the reason why we say diamonds are, forever or stable is because the activation energy is through the roof. The activation energy is big because it requires us breaking all these bonds and then forming these sp2 bonds. And so the thermodynamics part is this. The thermodynamics, we get our delta H here. Yes, our delta H here is good, right? Delta H here is good. Our delta H delta H is called a state function. Somebody remind me what a state function is. Yeah, it's path independent. It just depends on the final state and the initial state. And so here's the final state. Here's the initial state. And so when we're dealing with state functions, that's all we care about. But in kinetics, we need to know the path. In other words, we need to know the mechanism, right? Sometimes there's lower energy paths. Shoot, I forgot to do one. I forgot to talk about catalysts more. But that's okay. I'm going to go back to that. Talk about that now. But here we need to know the mechanism to see, and this is why we call it kinetically stable, because there's this huge mountain of energy this has to climb in order to react, right? There's the same thing here. There's a huge driving force for methane and oxygen reacting, right? But am I going to worry about it? If I fill this room up with methane, are we going to be engulfed in a flame? No, because, right, even though it's highly exothermic, methane and oxygen to CO2 and water, there is a hump we have to get over. The hump is not nearly this big because all it takes is a spark, A spark will cause a landslide to occur. Just a tiny spark gets enough to react, and that little bit that reacts releases so much energy that energy that's released keeps the reaction going, right? Sustains the reaction. And so methane and oxygen is what we call a metastable mixture. Hydrogen and oxygen does the same thing. If you release hydrogen into the air, is it going to explode immediately? No, not unless there's a hot surface nearby. If there's a hot surface or there's somebody smoking or there's a spark, then don't do it. But if there's nothing there to ignite it, then you're probably okay for a while, right? It's just going to react slowly. And so, we want to know both the kinetics and the thermodynamics. All right. Let me talk about catalysts briefly, because the catalyst will change this. If there's some kind of way to catalyze graphite formation, then we can drop the barrier considerably. Not that you want to develop a catalyst like that. But here's an example here. Here's without catalyst. Here's with catalyst. So with catalyst, it provides a totally different pathway to react with much smaller hills to climb. This is called a homogeneous catalyst because the catalyst and the reactants are in the same phase. It's a homogeneous catalyst. We also have heterogeneous catalysts, which are very common. In heterogeneous catalysts, the catalyst and the reactants are in different phase. And so this is a rhodium, a transition metal catalyst. A lot of transition metals are catalysts, like rhodium, platinum, palladium, nickel. They're catalysts, and one of the things they think is it's because of these d orbitals. Some of them have d orbitals that are empty. These d orbitals can accommodate electron density, and so we can get reactant molecules to dock, to this and facilitate electron rearrangements. And so here it helps change the electron density distribution of the molecules, which makes bonds easier to break. And then we have combination. For heterogeneous catalysts like this, they have certain steps, like this is absorption or adsorption, AD, versus AD. So adsorption, then some kind of rearrangement, and desorption processes here. You don't really have to know those. But this is a catalyst, for example, in a catalyst converter. Because in an engine, you produce carbon monoxide and oxides of nitrogen. And so with a catalytic converter, those get converted into CO2 and N2. Here. I want to talk about this next time. I want to talk about this acid catalyzed. Maybe I'll start with this tomorrow. Just go through it briefly. Acid catalyzed decomposition of formic acid. We'll look at that.
Computer lab tomorrow?
Tomorrow's computer lab again, so just go straight to the computer lab. Yeah. People make catalysts all the time, and a lot of people just do trial and error.
But that would be good, like, experiments to see that, so like some of the transition metals or certain things, right? You could combine them.
Right, different transition metal alloys.
Oh,
Try to find something that works better.
Okay.
Or cheaper, cheaper substitutes. Platinum and palladium is very expensive. So yeah, people make them all the time. This is a big thing in chemistry.
Fellowships at Columbia and Yale Medical School, an MBA at Boston University, Graduate School of Business Management,